Hi guys, this is the Athlete and Arithmetic's first video. Today, I'm going to showcase an unwritten rule of football with an equation. This is one that has been used in early rocket science, and it's so crucial to football that you won't see it the same again. That's right, today we're going to be looking at pursuit curves and interception optimization. In a game of football, passes are key. Simple passes are only good for short distances, as defenders are experts at tracking where balls will end up. This has inspired midfielders alike to come up with a clever solution, the curved pass. They allow a ball to get to a teammate without the defender getting near it. This happens for two reasons. One, often curves go around the defender and they can't reach it in the time that they have to get there. And number two, they can't predict where it's going to be. Expanding on that, defenders want to know where they have to be to meet the ball as soon as possible. Usually, straight passes allow this calculation as it becomes a simple problem of interception optimization. This refers to the process of intercepting an object with the least time spent, usually with the least distance. To give an example, let's say a footballer is at 0-0 on an XY plane, with a ball at 0-20. Say the footballer runs at 7 meters per second, and the ball is moving 3 meters per second to the right. Breaking up the footballer's speed, he moves in an X direction and a Y direction, which can be broken or resolved to their perpendicular vectors. Due to Pythagoras, if he runs an amount in both directions, he runs at an X direction squared plus a Y direction squared, and that will equal 7t squared. This will represent how he travels 7 meters total per second. We know interception happens where the X and the Y coordinates are the same between the ball and the footballer. So to calculate the footballer's total vector at that time, we can substitute in the X and the Y values. This will give us the equation 3t squared plus 20 squared is equal to 7t squared. Expanding this, we get 40t squared is equal to 400, or t squared is equal to 100. If we solve this knowing that t has to be positive as time can't go backwards, the footballer can get to the ball in about 3 seconds. This knowledge may seem irrelevant and complicated, but it's crucial to defenders deciding to go for balls. Now this knowledge may seem irrelevant and complicated, but this is the basis of defenders seeing if they can get to the ball before attackers. They do this by estimating this calculation inside their head. Most of them do it without even thinking about it. However, when curved balls are introduced, the equation becomes much harder. This is because the ball has a changing velocity, which basically means the speed is the same, but the direction is changing. This also makes it much harder for players to do this judgment in their head. This makes curveballs incredibly effective at confusing defenders and allowing crucial passes to be played. This was developed by and refined by the likes of Cruyff coaching for Barcelona. See, Cruyff had realised that football was just a game of mathematics. However, this opened up one problem. If the defender can't tell where the ball is going to be, how is the attacker or teammate meant to know? This leads us to the unwritten rule you never knew about: pursuit curves. This is where we chase an object by constantly moving towards it. This is different from what we just talked about, where footballers try and intercept the ball at a point by making a prediction on where it will be. This means that as the ball's velocity changes, so will ours. We see this all the time in football. When players are passed a ball, instead of going to where it will be by the time it gets there, they go straight to the ball and follow it in a more natural curve. This is calculated by measuring the player's vector with respect to time. We calculate this by dividing the total vector of a player to the ball by the magnitude of that vector. And here we get the unit vector of that direction. Then we multiply it by the speed of the footballer, and we get our vector. For example, if a ball lies at 7-9 on the XY plane, and the player is at 1-1, the total line of sight vector is 6-8, divided by the magnitude, which is 6 squared plus 8 squared, square root, which is 10, we get his speed times the unit vector of 0.6, 0.8. This is his vector for that instance. If you haven't done this yet, and you want to never miss a ball in football again, we recommend that you measure your own speed so that you can do these calculations in your head better. Let's say he runs at 5 meters per second. His vector for that moment will be 3, 4. The calculation for finding where a player will meet the ball on a pursuit curve is far too complicated for me to explain, and far too complicated to judge. This makes it so pursuit curves are most common for unknown ball trajectories. Early rockets used pursuit curves as they didn't have the digital computers or sensors to do the complex equations for interception optimization. However, most modern rockets use something closer to interception optimization, as it is very inefficient compared to that of a straight line. This highlights a key fact of pursuit curves in football: they're draining. Often, defenders are too tired to chase a ball in an inefficient manner, in which if the passer is good, they will never get anyway. The ambiguity of curved passes is a key reason why they are so good at tiring out the other team. This is only amplified when it comes to goalkeepers coming out or not, as if a curved pass comes in, they have to make a split decision. If they come off their line, they might be able to get to the ball before the attacker and stop the attack. The goalkeeper could also not get the ball before the attacker, and this would give them an easy opportunity to score a goal. Goalkeepers have less chance of getting this calculation right when it comes to curved passes. For example, in the 5-4 madness of Barca versus Benfica in the Champions League, ter Stegen comes off his line when someone crosses the ball in. He does this thinking he can get it, but the player passes with a curve so that Artukoglu gets to the ball before the keeper. This puts ter Stegen in a terrible position where he eventually gives away a penalty. Here, ter Stegen used a pursuit curve to follow the ball as it was easier, but it caused him to misjudge his timing, and he paid the price. You know what he should have done? He should have done his pursuit curve calculations, or stayed on his line. Thanks for tuning in. We'll speak to you tomorrow and in the future with more athlete and arithmetic. Bye.